Today we're extremely pleased to have Dr. Irfan Siddiqi visiting us. He has made seminal contributions to quantum measurement science, including real-time observations of wave function collapse, tests of the Heisenberg uncertainty principle, quantum feedback, and the development of a range of microwave frequency quantum noise limited analog amplifiers. His research has laid the key foundations for the advancement of quantum information processing, which is of course, has for a long time been of great interest to many of us at the lab, and is of increasingly of national importance and a focus of a growing focus of national efforts. Dr. Siddiqi received his undergraduate degree in chemistry and physics from Harvard and his PhD in applied physics from Yale, and then joined the physics department at UC Berkeley in 2006. He's also a faculty professor at Lawrence Berkeley National Laboratory. He runs the Advanced Quantum Testbed at Lawrence Berkeley Laboratory and is the founder of the Center for Quantum Coherent Science at Berkeley. He's an APS fellow and the recipient of many prestigious awards for his accomplishments, including being distinguished as a very highly regarded teacher and recipient of the 2016 Distinguished Teaching Award at UC Berkeley, which is its highest honor for teaching. We're very grateful for the opportunity to learn more about Dr. Siddiqi's research and thank him for joining us today. Please join me in welcoming him.
Thank you so much. Okay. Well, thank you so much for the warm welcome. It's great to be here. And I have to apologize to all my colleagues, even though we're very close, but I haven't visited this institution so much. So thank you so much for hosting me. Is the sound okay? Everyone can hear at all levels here and also in absentia? Good. I want to start by taking about 10 or 15 minutes to really look at the foundations, if you like, of quantum information science. And the reason I want to do that is I want to share with you a little bit of my own thoughts about the field. I started working on superconducting qubits before they were superconducting qubits. Right? They were circuits that we were using for sensing and for other things. There's been a tremendous transformation how that particular field of science has become an integral part of quantum information science. And what that's led to is that there's a lot of promise and there's a lot of promises in the field. And it would be important for us to look at, where are the scientific challenges and where do we hope to be in the next decade, in the next 5 decades. So that's a little bit of the spirit of the talk. Okay. So I want to start off with this image saying that this to me is really why there's really a revolution in place at the moment, where mechanics like myself can now saw into quantum mechanics. Right? And that's a capability and a set of capabilities that is rather new to us, and it should be rather transformative, even if we don't realize any of the promises that we have today for quantum information processing. I think the best of quantum is still yet to come. We now have access to a toolbox which is unprecedented, and we're still trying to figure out what these tools are really good for. So I want to start the discussion by saying revolutions in quantum theory start really with this idea that the world is granular. Okay? And this was rooted in a very physical problem, the problem of the potter. Now, how do you understand black-body radiation from clay objects? This was completely inaccessible to classical physics. So the idea that the world is grainy really fueled that theory and that explanation, but it came with excess baggage. Right? And all this excess baggage we debated for many decades. Is the world really entangled? Does it entangle over the size of the cosmos? It drove Einstein wild, as you know, to think about these things. And are there limits to this entanglement? And in my mind, the second quantum revolution is where we can say the world can be entangled on demand. Right? And that's a very, very radical change in terms of the technology and the physicality that we have access to. And in particular, it brings up new sets of physical questions. It's interesting to see the juxtaposition of high-energy physics then and now. High-energy physicists like Einstein were thinking about, well, can entanglement persist over the size scale of the universe? High-energy physicists of our era are thinking, well, if you don't have this entanglement, the universe falls apart. Right? That's a rather different change in philosophy. So there's new sets of questions that are also coming up and driving this field. So in fact, what is it that we're trying to achieve in quantum information science? We know that the world around us is quantum. There are signatures of this everywhere in materials that you use. And in particular, I wanted to choose this image because I've been having trouble with my shoulder, with a nerve that's pinched. So I thought, well, the MRI is absolutely quantum. In fact, you look at the water molecules that are there, you polarize them, okay, and of course, your measurement of the spin will yield something which is up or down, so to speak. What's different, of course, in MRI is that you can prepare a superposition, right, which is a spin pointing sideways. And the relaxation of this spin will depend on the tissue around it. Of course, we access this in a sort of ensemble sense. We're not really looking at the individual water molecule. We're looking at a lot of them that are there. And in fact, herein lies the idea that quantum systems can exist in many different configurations, even if you can't observe all of them. Okay? This is really the intellectual driver of quantum information science. Okay? You have a spin, you have an entangled ensemble, the number of combinations you can have is a lot, but you just don't see all of them at the same time. Right? And one has to pause, and I'm pausing, because absorbing this classically is hard. We're used to being able to see under the hood. You see all the mechanics that are there, but you can't look at them. But you can use them. And that's really the challenge of quantum information processing. How do I set up those algorithms, those protocols, to sample this large space that's there in a way that's actually meaningful? Okay. So if we were to try to build a quantum computer, let me sort of walk us through this NMR analogy. But we build it one spin at a time, okay, one molecule at a time. Unlike MRI, which measures average properties of a group of spins, we need to address each one of them individually. So let's imagine I put them on a grid like this. And in fact, if I measure any particular spin, let's say that one shown in red, when I measure it, my measurement will simply be either up or down. Okay, in this case, it's up. Right? I picked that red one. Now, if I cover it up, in fact, it can take on any combination of up or down, because that spin can point anywhere in my three-dimensional sphere. So you see, that's an example now of this complexity which is hidden. If I don't measure it, there are many more outcomes that are there. So in fact, this spin would be described by a pair of numbers, A and B, which would tell you how much is up and how much is down, say. I can do the same with its neighbor, and I'd have two numbers, C and D. The interesting question is now if I start to couple them, right, and start to put them together, then how many combinations do I have? My basis set you can come across by simply multiplying the two things together. Right? So you would get something that has these coefficients, A times C, A times D, B times C, and B times D, corresponding to the combinations up, 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 down, down, up, and down, down. Okay? But what I want to show you, the real power of entanglement here, this is a superposition state of up and down. What if I have a superposition of these four combinations? So look at this state. Up, up, plus down, down. This one cannot be described as this product. There's no combination of A, B, C, or D that will give you that state. Okay? So for example, if I want to kill these two terms in the middle, if I set A equals to 0, then I lose the AC term, which is what I need. And if I set D equal to 0, I lose the down, down term. So you see, this is an example of an entangled state. Right? This is where you cannot break it apart into two pieces of the system. It has to be, in fact, a unique single object. And this is really what we're talking about with entanglement, saying that the number of parameters you need to describe such a system grows as 2 to the n instead of 2 times n. Right? This is a product state which would scale as 2 numbers plus 2 numbers plus 2 numbers. But of course, in the quantum domain, as I showed you, if you only looked at 2 times n, you couldn't describe these very simple states that are there. So that's really the power of quantum entanglement. And in fact, you hear these statements that if you have, let's say, of order only 300 elements that are fully entangled, the number of parameters you would need to describe this 2 to the n object, they don't agree. So they're honking in, with their opinion. So the number of elements that you would have with 2 to the n, with n being about 300, is more than the particles in the universe. This is a true statement, right? That's 2 to the 300. So the idea that how many qubits would you need to do something meaningful and powerful, one shouldn't think about this in terms of classical transistors. You get a space which is very large and grows exponentially very rapidly. Right? This is at least to temper expectations, since experimentalists like me only have about 10 qubits. So it's not that we're 9 orders of magnitude away from the transistor. Maybe we're only a few orders of magnitude away at some level. Okay. I wanted to jump to this slide, saying, well, what could you do with it? So I'm going to take from this very nice report that came out about a month ago from the Boston Consulting Group that said, what's the status of quantum computing? Where are we going to go in a decade? And I think it's a very nice report. Right? It summarizes a lot of basic points. So the things that we know how to do at the moment, or we think we know how to do at the moment, in this domain are listed here. We think about pattern detection, Fourier analysis. We think about efficiently searching databases. We think about cost optimization problems where you're trying to find the minimum solution for something. And we're going to try to do matrix math. Okay, that involves linear algebra, machine learning diagonalization. If you take these tools together, then you get these kinds of applications that are envisioned. And they're pretty broad. Right? Machine learning and artificial intelligence, logistics, scheduling, aerospace, drug design, materials analysis, so on and so forth, network design, communication. And there's a lot of companies now that are on board. Just to show you, there's a lot of interest in the field. And I'm going to drill a little bit into some of these applications and even show you 2 calculations that we have sort of performed very recently. Okay. What's the challenge? Well, the lifetime of these systems, this characteristic time scale over which quantum mechanics decays, is still a bit short. And that limits us to only having, let's say, of order 10 logical gate operations. So we'd like to really get above 100 operations. We'd also like to scale the classical resources in an efficient way. So these are 2 things that are slowing us down a bit in the road to practically implementing these devices. Okay. Are there any questions up to now? Feel free to ask questions along the way. Okay. So what are physical implementations of quantum bits? It's true, everything around us is quantum mechanical, but the reason some systems at the moment are more well suited towards information processing is that we're able to isolate them from their environment. Right? The name of the game is that if you have a quantum system and something measures it, you necessarily interact with that measurement device and you see some kind of classical behavior. You remember I showed you the single spin in your MRI? As soon as you measure it, it's either spin up or spin down. That's the observer doing the measurement. If you have any defects in your environment, that environment is making the measurement, but it's not sharing the information with you. Right? That's the challenge, making sure that you have a handle on all the information, no leaky channels. One can imagine scaling to some ultimate limits of silicon technology, where you go to individual electrons or individual dopants, and that's shown on the upper left as dopants in silicon and diamond as a technology platform for QIS. One can imagine the optical version of that, if you like, with individual atoms and ions being trapped and laser beams addressing them. One can think of the photons themselves, shown in the middle, as photonic circuits, where waveguides induce interactions between photons. Or one can think of electrical circuits. And in particular, for us, we work on superconducting devices that are in the lower left panel over there. Okay. There's also the same report gives you a nice graph about these various technologies. And they use the terminology, which I think in this lab is probably very common, TRL, figuring out where are we. And in fact, superconducting qubits are listed as TRL5. Okay? Just to give you a sense of what has been developed and what the major challenges are. And the other technologies are also listed in various levels of advancement. So again, I encourage you to find this free report on the web if you want just a very quick primer of what's going on. Okay. Well, what do we hope to achieve with qubits? We can start with 1 qubit, which is at the very top. And 1 qubit or a few qubits are a very good way to communicate information securely. I show you the picture of how the Greeks used to communicate many millennia ago with that piece of wood and leather on the top. That's a Siddiqi. So this is a very interesting object. If you would like to send a message to your compatriot in a war against Sparta or some other particular city-state which is there, you would put it on some leather strap, and you roll it around the cylinder. Okay? And if you pick the cylinder of the right size, when you roll it around, you can read the message across the line, much like the Enigma machine, of course, of the 50s, 40s and 50s. So quantum mechanics, of course, also allows you to have a key in the photons that you use, but it's a very special key. If you measure those photons, you decimate the key, and someone knows that you've tampered with the key. But nonetheless, with a few qubits, you can start to have this physical encoding of information in communication. If you're in the era of somewhere between 1 and 100 qubits, this has been termed NISQ, not to be confused with NIST, which is very different and very precise. NISQ is very noisy, right? This is the noisy intermediate scale quantum era. And what this is really code word for is the idea that we're not doing error correction on these bits. Right? If I have these physical elements and they're quantum mechanical and they live for a short period of time, what can I do with this? Right? What algorithms can I run on this? And I think the critical point here is that the era is characterized by somewhere between 10 and 100 physical qubits, so individual little circuit elements. They have minimal error correction, as we said. They are also purely quantum and hybrid algorithms. I'll show you what that means in a second. It may not be critical to solve all your problems quantum mechanically. You may only want to solve the one hard step in your algorithm by quantum. That's much more efficient use of resources. And we have less than 100 logical gate operations. So what could you do with this? I think it's exciting because soon we will cross this boundary where you will build a machine that cannot be simulated by classical computers. What this machine will do is debated, but you will build something that for sure you have no hope to solve with the classical code at the moment. So that's exciting in and of itself, saying that how do you actually validate, verify, figure out what you've built? You will also see the first quantum computations. They may not change the way you surf the web or your children surf the web or do other things, but they will do something. Right? They will compute something. I think what's very important for me is you will reveal the scaling of quantum advantage in the sense of what quantum is really good for and what classical resources do you need to actually realize a quantum machine. This to me is a tremendously, as a physicist, tremendously important question. Because if you think back to Einstein, Einstein was troubled by this idea of communication at galactic scales. But of course, with John Bell, we understood that you have to send a classical photon to have that information go across. And that brings reality into the world. In quantum computing, I see the same problem. We say we have this perfect qubits. You have this exponential growth of the phase space. I fed you the same party line in the beginning. But at the same time, you need to correct for errors. You need to stabilize the information. And that's a lot of classical resources. And once you factor that in, what do you have left in terms of the quantum advantage? Right? So I think to me as a physicist, that's a tremendously important question of saying, how do you stabilize? Is it really possible to stabilize a quantum system at that level? Okay. And I think we'll also see a growth of resilience in our error-correcting codes and our protocols. Somehow we have to live with noise. Okay. And finally, I wanted to put this out there. I think you'll see a growth of new classical computing hardware. We have been in this model of digital computing for a long time because we have figured out how to process sand to an unprecedented level of accuracy in terms of flatness and low defect count. But if we are unable to continue working with sand at the level of 10 nanometers, then there are other architectures that are still classical that are definitely viable. They are found in the books of computer science and have been shelved away for many decades. So quantum is also telling us what it's not good for, which means there may be a lot of good classical things that come out of this also. So just to give you a broad scale of perhaps what one should expect in the next 5 to 10 years. Okay, so I want to delve a little bit into the physics now of the circuits that I work with. How do you make an electrical circuit quantum mechanical? Because when we go to engineering classes, we learn about Ohm's law, Ohm's 3 laws, right? V equals IR, I is equal to V over R, and R is equal to V over I. There are 3 laws of Ohm that you learn about, and none of those quantities are quantum mechanical. Okay. You go to quantum class and you learn about atomic physics and so on and so forth, and these are 2 different subjects. But in reality, they are the same subject. So let me sort of talk a little bit about this. So here's an amplifier, highly classical in the way we think about circuits. It's a combination of R's, L's, and C's, right, with Ohm's 3 laws. And you excite with voltages or currents And classically, we take it for granted that R, L, and C can take out any value. Right? The textbook is not telling you that somehow you're restricted in your choice of R, L, or C, aside from some physical constraints. If you want to make a tera-ohm resistor, this is problematic. But usual resistors have no problem in turning the slider on the resistance value. Quantum mechanics says these are fundamentally discrete. If you look hard enough, you should see some granularity there. So where is this granularity? This granularity becomes apparent at the nanoscale, for one. You shrink things down, and you start to see some restriction on the value of these elements that you can have. For example, the capacitor. Okay. This granularity is such that the level spacing typically, even for reasonably sized objects, 10 nanometer sized objects, is much less than 1 degree Kelvin. So if you'd like your thermal energy not to smear you out, you should cool to a temperature below that. So that mandates really cryogenic operation. Moreover, you need to isolate from the complex environment because that's what's going to measure your system and always keep you in the ground state. So if you'd like to make some very exotic quantum state, you need to make systems that are small, cold, and isolated. And I made this statement at a keynote a few weeks ago, and I hadn't realized that there was a big chuckle from the audience, because small, cold, and isolated is probably not where human beings like to be, right? So I think the real challenge is to make your system small, cold, and isolated, where the observer is still human, warm, and interacting. Okay. And that's really the challenge. How do you actually store information and get something of value out to the external world? Okay, so the history of superconducting qubits. In 1999, the first superconducting qubit was demonstrated in NEC labs. And you can see these are the quantum oscillations they published in Nature. Okay. What's interesting to note is the time scale. This is measured in picoseconds. Right, so those oscillations are very short-lived. Fast forward to 20 years, and in particular, you have this beautiful work coming out of Rob Sholkoff's group at Yale. In fact, the same oscillations are there, but now we're looking at things that are on the 100 microsecond time scale and beyond. So that's a large number of orders of magnitude improvement in coherence time. So this minimalist qubit, if you like, this structure really is elegant in that it's a tunnel junction with ears, which allow you to really realize a dipole. Okay? And I think one of the tremendous outcomes of this research is we realize that tunnel junctions made in aluminum oxide are compatible with milliseconds of coherence time. Right? And I think that was something that was simply not appreciated 2 decades ago when people were still thinking about, well, are superconducting circuits quantum at all? Right? Atomic physicists would always snub their nose at us, saying that you don't really have quantum systems. But I think we've gotten over that. They are really quantum, right? As is everything. The goal is to make the lifetime long. So the upshot of this is that there's also many other designs to pursue. So I will talk about one qubit design. You have a different platform, a very rich platform that's being undertaken here at Livermore, and there are other designs also to be explored. So we're not done yet with the design of the qubit. Okay. So how does this work? Here's my RLC circuit. Okay. This is an oscillatory circuit. A classical harmonic oscillator says all energies are allowed. Quantum mechanically, when we solve the oscillator, we know that's not the case. You quantize the energy, right, in the quantum version. And moreover, you can think of that as an artificial atom with spacing in the 1 to 10 gigahertz range. So it's a harmonic oscillator with frequency in this range. We also think about the effective damping, and this is caused by fluctuations around the oscillator. We add a tunnel junction. So here's an aluminum oxide tunnel junction, a 500 nanometer scale bar there. And what this does is it adds anharmonicity to the time-tested harmonic oscillator. Okay, so those levels now are not equally spaced, so you can isolate 2 of them and call them a qubit. Okay, so this is the basic recipe of superconducting qubits. They are simply particles in a cosine box. We learn about a square well potential. This potential is the cosine potential, and you quantize the levels. The tricky part is what are all the ways that this circuit will relax? Okay. The first thing that you note, unlike real atoms or naturally occurring atoms, they are well coupled to a 377 ohm environment. So if you take a circuit, it's of order, has some characteristic impedance, it will radiate its energy away. Okay. So as soon as you start to put wires on your circuit, it's game over because everything's going to radiate out. Moreover, you can think about, well, transmission lines, this is good in the microwave, but they also have some kind of 50 ohm impedance. So one has to be a little bit careful of how to design these circuits. So the recipe that is typically shown here is that you put it in a single mode cavity. So the cavity goes ahead and isolates you to, let's say, the fundamental frequency, and also gives you a good way to get signals in and out. So allowing you to preserve coherence, but also measure as you need. Okay. So this is very much the spirit of cavity QED, right? An atom in a cavity and the light-matter interaction that occurs there. So from the engineering point of view, you shoot a signal in, a microwave signal in through a circulator, and you look at the signal which is reflected out, and there's a phase shift depending on whether your qubit is in state 0 or state 1. So now I'm making a mapping from something which is deeply quantum, the idea of a spin, to something which is very measurable. And I take my microwave device, I put a light field in, and I look at the phase shift upon reflection. Typically what will happen is you can look at the quadrature phase and in-phase components, right, the sine and the cosine of your AC signal, and they will tell you about the system that you're looking at. But there's a challenge. It seems too easy. The information that's encoded at the fundamental level is at the level of 1 microwave photon. So if you would like to make a very high quality measurement of the signal, you need to measure 1 microwave photon in the background, and that's quite hard. And one typically does not buy amplifiers to do this. Okay? Most amplifiers will be noisy. They'll amplify the signal, but add 25 photons of noise. So if you take your best HEMT semiconductor amplifier, it will add 25 or 50 photons of noise. Okay. So a lot of our time was spent building these microwave amplifiers, which we've also shared with other folks in the community. Here is version 17 of a parametric amplifier that we built at Berkeley. With this, we were able to do a number of things. If you think of your superconducting qubit as an artificial atom, it has 2 levels, shown here. When an atom relaxes from its excited state, it emits an optical photon. Okay, and people can go ahead and observe that. When our system relaxes, it will emit a microwave photon, and we were not able to observe that at the level of 1 photon. We would always measure an average decay. And that's what's plotted here on the upper right. You would see the average population of the excited state go down in some exponential fashion. But here's where we ran into trouble with our cynical physics colleagues, our atomic physicists. They said that's exactly what an LC circuit does. Right? There's nothing quantum about that. Right? You charge up a system, it's a pendulum, its amplitude will go down. Right? But we, of course, had true faith in the quantum mechanics of superconducting circuits and said what's really going on is that on some stochastic time scale, you have relaxation. Right? And on average, that's what that ensemble does. And if I were really able to observe 1 click at a time, this decay, I should see the quantum mechanics of that distribution. So as soon as we optimized these amplifiers, the first measurement we did was to measure the individual emission events and histogram them. And I want to show you that data. So here's that real data, bidding them 1 at a time as they come through. And you see the histogram that you get. You get the same decay curve. Right? So this was telling us that, yes, quantum mechanics seems to be working. Right? If you actually go ahead and look under the hood, you will see these individual events that are there. We went a little bit beyond this, saying that, well, if you look at any one of those clicks, how does your spin go from a superposition to an eigenstate? Now, the founders of quantum mechanics were very clever. They have made never any mistake with their postulates. They've always said, if you measure a quantum system, you will measure an eigenstate, absolutely correct. And you will measure, let's say, in a 2-state system with 50-50 probability, spin up or spin down. They never said anything about instantaneity. Do you see it immediately? How long does it take, to make the measurement? What's the path that you take? So we took these amplifiers and started to measure very slowly and weakly, saying that let's look at the information stream of 1 click in real time, and we slow it down. And that's what's shown here on the lower right. I prepare a spin in a superposition in purple, and I'm going to sort of take the information that comes out of the system, update my best guess as to where the instantaneous position of this spin should be, and that will be an individual quantum trajectory. Okay. And that's real data showing you one click. And it's quite wild. You see the system goes up, it goes down, and then after a while it settles on an eigenstate, in this case the up state. So what I wanted to show you with this windup is to say that there's this back and forth between fundamental questions in quantum mechanics and technologies. As we start to probe deeper and deeper, we start to build the tools of building, let's say, a quantum computer or a machine that does quantum information processing. So this is the measurement part of it. Okay? And in particular, we can now think about life beyond a few qubits. What can you do if you start to have more than 1 or 2 or 5 qubits in an ensemble? The first thing is we need to produce these with enough robustness that we can actually try to form a system. Okay, so this is a picture of our fab facility at UC Berkeley. It's a class 1 clean room that we have set up solely for the purpose of producing superconducting qubits, and we turn around a 6-inch wafer of devices in 2 days. Okay. And there's a little histogram showing you about 2% spread in the parameters of the tunnel junctions in this array with a 99.4% yield. So this is a good start. We can't be in this mode where one device works and the next one doesn't, and so on and so forth. We'd really like to get into some robustness so we can engineer this. Well, what about readout? That same amplifier technology that I showed you has been expanded now into more wider band devices. And I wanted to show you this image from the National Strategic Overview for Quantum Information Science. There was a picture of an amplifier. That's our amplifier that we built, right, for making lots of these measurements at the same time. And I wanted to show you the data that goes along. That's not in the report, where we actually go ahead and use the amplifier to measure qubits. So here is a simultaneous measurement of 10 qubits with 3 nines measurement fidelity. So again, showing you the basic tools of looking at the quantum inner workings of the universe are pretty useful if you're actually trying to solve a very engineering-oriented problem. The next step in this process is to think about, at least for us, how do you get away from the 3D cavity model? I showed you this very nested, very nurturing environment of taking your quantum bit and putting it in a box. This is great when you don't want to talk to your qubit. The challenge, of course, is when you have many qubits, how do you scale those boxes? And there are ways to think about that. But for us, we wanted to put all that circuitry on a planar chip, okay, in this case. So here's a chip with 8 qubits, and they're connected in a ring. So each one of these boxes here, the pointer is not very intense, but if you look up here at the upper left, that's 1 qubit, next one, next one, next one. They're in a ring. And in fact, we measure coherence times. This is actually an old slide now, well in excess of 100 microseconds. Here's data for 60, 70 microseconds. If you remember, I gave you these 2 endpoints. The first chip had this 1 nanosecond coherence time. The 3D cavity had about 100 microseconds. So we're starting to get up to reasonable times, even in planar chips that are approaching these cavity type of numbers. Okay. What's the challenge in actually building such devices? Well, the first tricky part, and I want to sort of speak to this audience who thinks a lot about materials and simulating materials defects and materials problems, is that you have a lot of interfaces. Right? That minimalist qubit simply was a little dipole in a box. Now I have the silicon chip, all the metal layers, all the things inside. And the question is, how do you diagnose all of these defects in an easy and robust way? So this was, I think, the simplest example of material science engineering from our side, which was to put a drop of water on the chip. So one of my postdocs, who's now a professor at MIT, is very clever, who was doing the fab of these devices, was suspecting that there were little monolayers of oxide at the various processing steps. And he pulled out this old paper from '74 that said the wetting angle of a drop of water changes depending on the number of monolayers of oxide that you have. Again, there's a picture of it. And what he did was start to put water drops at the various fab stages of this process. And in fact, he could, with selective etching, change the wetting angle. That's just a simple camera picture. And what that did, you can see there, it changed, in fact, the T1 time by a factor of 2. So that was us just doing water-induced metrology of the surface. But to give you an idea, there's a lot of room, right, to improve materials in this domain, to figure out what those interfaces are, what that noise is, and so on and so forth. Moreover, I'd like to show you data that you don't always see in the literature, Well, what is the distribution of numbers that you measure? Let's imagine you measure a 50 microsecond lifetime. Is it always 50 microseconds? What's the statistical distribution, and so on and so forth? So here's data for 4 representative qubits from that chip. The green one is the lifetime, the T1, the spontaneous emission lifetime of the qubit. And you can see there's a histogram on the upper left for Q0, about 40 microseconds, 60 microseconds for Q5, 60, 70 for Q6, and let's say 50 microseconds for Q7. All the histograms look different. Right? So what's that noise environment like at different points on your chip? It's quite complicated, right? And it's not the same. Even if you were to look at the mean value, you would think everything is controlled, but there's still a lot of complexity there. Moreover, look at the dephasing times, shown in this yellowish color, pinkish color, the echo times. Q7, look at it, it's 80 microseconds. As you get into these long times, you also have broad histograms. So again, there's a lot of materials issues to think about in these quantum systems. Okay, what are those noise processes? Are there noise processes that are inherently quantum, not classical? A tremendously important question. Okay. Now let me also think about, well, let's imagine I take this data and take the engineering viewpoint. Let me try to now build a 100-qubit machine. How likely am I to succeed in that 100-qubit machine? Well, I have to talk about what kind of gate you want to use. You want to couple qubits together. So a gate which is commonly used, and you see in the literature, this is called the cross-resonance gate. So let me try to illustrate this gate. I need one more pendulum. I will use this and promise not to drop it. Here's the pendulum. Here's another pendulum. Okay? You have different frequencies. If you excite this pendulum at the frequency of this one, it's not going to move a lot unless they're coupled a little bit. Okay? And this is called the cross-resonance gate. You force one pendulum at the frequency of the other, and you induce a little bit of oscillation if there's coupling between them. Now, what are the things that are going to be critical in this cross-resonance gate? Well, where do you park the 2 frequencies? If they are very detuned, they're not going to excite each other. They have to get reasonably close. If they're too close, it's too much. Then they'll be coupled all the time. Okay. So what we tried to do was this calculation that said, well, let's imagine the spread of parameters I have in my junctions. Let's imagine the right positions for all of these oscillators. And that's shown up here. Right? Given the anharmonicity of your system, shown in alpha, then there are allowed regions, right, shown in white, shown in this lavender color. Everything in white is not allowed. Okay, those are not the frequencies where you want to park your system. So now I can make a map and say if I put 8 of them on a ring, put a 2% distribution in the parameter spread that I get, and I use a Monte Carlo simulation to figure out where I should lay out these qubits, you know, how many of them will work with this junction yield? It turns out you only have maybe 10% at best. Okay. So you make a, let me back up on this one for a second. You make a chip with 64 qubits, 64 samples of 8 qubits, and at best, you will only get 10% that are there. Now let's imagine I make it for 100 qubits or 100,000 qubits. You can do the math, right? So this is again telling us we need to think about architecture. We need to think about how to make these noise robust, more complicated structures, even though it's very easy to try to engineer simple systems on day one. Or you can be like some of my graduate students and say, well, what this means is we just need to make better junctions. Right? If you have a 1/10% spread in your junctions, life gets better. And I'm the old cynical physicist saying this is not going to happen because it's so difficult to do. If you look at a FIB cross-section of your tunnel junctions, you can see there's the interface, and it's completely jagged. Right? So even though your tunnel junction on the top surface looks smooth, actually the interface is quite jagged. What are we actually looking at here? What are the materials? These are false-colored aluminum with aluminum outside invisible at the interface. So again, saying that as you dig deeper, there's yet more material science issues and challenges of how to actually work with practical materials to get the right robustness. Okay, well, let's imagine you have the chip. How do I go ahead and wire it up? This simplest qubit has the design, in fact, of a tunnel junction with 2 ears. How big do you make the ears? Right? How big do you make the junction? You have to balance radiation versus surface loss. And what I show here on the bottom is a balance of radiative losses and surface losses. And this tells you how big you want to optimize the objects that you have on your chip. You have to think about where are all the spurious microwave modes. So there's a lot of modeling of the microwave structure that's there. And you need to think about crosstalk. Now, this is an interesting plot at the bottom, because we all get in trouble as experimentalists for this. Those are the 8 qubits shown there. And I'm looking at one feed line for number 7. And there's a little pad at the end of this feed line where you would bond the wire to send the signal in. So the thing you can ask is, how big should I make that little bond pad? Okay. And if you're a graduate student, I would make it big, so it's easy to actually contact. I would make it a millimeter big, and millimeter is not that big, but at least it's a millimeter. If you make it 1 millimeter big, the crosstalk shown here for a 1 millimeter bond peg is of order unity. So all your qubits will talk with order unity crosstalk, and there's no hope to make that chip work. Okay. So in fact, they're 100 microns or smaller at the moment. So a lot of very subtle engineering that goes in the chip, because your design rules are very different. Right? The design rules for quantum science are very different than classical VLSI. Okay. And then you put them in your fridge. That's 1 meter scale bar roughly across the fridge. So it's a rather large object. This is the wiring diagram for 1 bit when done properly. Okay. Let me back up a second here. There. So these are discrete components. You buy them. They're expensive. What, $10,000 a channel? Something of that order, if you put in the HEMT or what have you. So one has to think about that for scaling and multiplexing. But moreover, here's a plot where we went through 16 different combinations of room temperature filters to show you the optimal time of operation. So you see, it's same device, just different filters. And in fact, if you look at, again, the echo time shown in this beige type of color, you see with not enough filtering, the lifetime is about 10 microseconds, if not smaller, and we push it to 70 on the bottom, changing nothing in the qubit. So telling us we really need to understand what are those components that are robust in the wiring of these devices. And moreover, beyond simply reducing complexity, what's the actual signal type we're dealing with? And what I'd like to propose is that we have a really new signal type. It's not digital, it's not analog, it's quantum. And the question is, how do you convert from quantum signals to analog signals to digital signals? And how do you do it efficiently, and where do you do it? At what temperature? So if you look at this color-coded diagram, again, this beige kind of teal kind of color, beige kind of color at the bottom is all quantum. There's too much quantum in that picture. Everything cryogenic is mostly quantum. Then the green stuff is analog, and the blue stuff is digital. Right? So this is not easily scalable. Okay, so one has to think about the quantum signal as an entity to itself. How do you interface it with the outside world? Okay. So in terms of the tyranny of wires, we do think about FPGAs. These are things developed by our accelerator group. Okay, and they're going ahead and trying to scale in a cost-effective way with optical interconnects, ways to control these bits. Okay? And what I want to show you is that the problem of information is quite heavy in the quantum domain. Let me try to illustrate this. It's great to think about this entanglement. I showed you this 2 to the n. You make a small object, a chip, it has all this information. But the Achilles heel is if you have to actually measure those 2 to the n degrees of freedom. This is absolutely not possible. If you could measure them, you would just use your classical computer. So the general high-level idea is that you initialize the system. Right? There's someone on the left initializing the system. And your quantum processor samples this 2 to the n space. You don't ask any questions about what's happening. And at the end of the day, you get an answer. But the problem is this requires perfect performance on your quantum system. So you do actually need to perform tomography to check if it's really quantum, to check if it's a state that it's in. You do need to correct for errors. You need to measure some error syndromes and correct for them. You do need to, in fact, go ahead and diagnose subtleties about the logic. And that requires lots of gate operations. You may want to do feedback. Okay? So all of these things are data heavy. And classically, that's a lot of data. One can think about machine learning. Can you use machine learning to help this process, either in a purely quantum fashion or a classical fashion? Right? Tremendously open question in the field at the moment. Just to give you an example, in the problem that I talked about, here's the quantum system that I initialize, and then it takes some trajectory. Measuring those trajectories is very heavy and requires a lot of mathematics and a lot of data. We applied a recurrent neural network to try to learn quantum mechanics. So we asked the question, can you teach a machine quantum mechanics without telling it any of the rules of quantum science? Okay? Take a black box. This is the evolution of my spin. Okay? What the mathematicians have taught us is that you get a rule for the probability of finding the state in a certain value, conditioned on the initial part, the measurements, and so on and so forth. And it's a hideous formula. Hideous. Right? You'll have to write the density matrix and update it, and think about Lindbladians. You draw all the curly little dissipators and so on and so forth. Jonathan Du Bois is here. I'm sure he loves this, right? This is great to think about dissipation, but it's a lot of work. And the question is, can you teach a neural network? Can you train it based on some data to learn the rules of quantum mechanics? Okay, and the answer is, it does great. So we fed in this trajectory data on a K80 GPU on an RNN that you use, in fact, for speech recognition with Google Translate. So we just downloaded the free package, ran it, great. Absolutely great. So this, again, brings up the idea of how do you handle big quantum data? This, in and of itself, is an important problem. Okay. So at the very end, just to take a few minutes to wrap up here, starting to compute. Can you do something with these systems? This is a plot showing you what we understand at the moment of different types of quantum algorithms. There are certain algorithms that go ahead and have bona fide speed up over classical counterparts. Okay, so Shor's algorithm is shown here. Right, if you'd like to factor a number into its primes, this will be better than any known in-class classical solver and be exponentially faster. Challenge, of course, it's hard to implement. A lot of resources are needed. There are algorithms on the upper left which simply do not have, at this time, we don't know if there will be a speed up, but they may be really useful for understanding the chemistry of certain molecules, energy level structure, so on and so forth. So there's this dichotomy at the moment, right? What can we learn from these near-term algorithms, and how do we implement these longer-term algorithms? There's no, at least in my mind, there's no silver bullet yet that says this is the one algorithm you should go and solve today. So I'll show you this chemistry algorithm and then finish up. There is something called the variational quantum eigensolver, VQE. You'll see this in the literature quite a lot. This algorithm has the following idea. I want to minimize some cost function, which I write as H. Okay? So H may encode, let's say, the energy structure of a molecule. I want to find the minimum energy. That's the configuration. Or it may encode, for example, the coupling between highly correlated molecules. Okay? So this is what you would use for drug design, nitrogen fixation, so on and so forth. Okay? What's the procedure? Well, you first have to map this cost function H to some kind of Hamiltonian in your qubits. Okay? You prepare the state. So number one, you select a set of parameters. You prepare the quantum state. You measure it, and then you adjust the parameters till you find the minimum. So there's a lot of mathematics on this. Let me give you the experimentalist viewpoint of how this works. This is my quantum box. It has 5 knobs. Okay? If I turn all these 5 knobs, I will see all the possible states of my system. Okay? So the problem is I just need to find the combination of knobs that will give me the ground state. Everybody with me on that? Quantum box, 5 knobs, spans the space. That's exactly what this thing does. It says put the knobs in some configuration, measure the energy. Turn the knobs, measure the energy again. If the energy is lower, keep turning that way. Okay? And at some point, you will find the minimum energy. That's it. That's how this algorithm works. Now you can immediately think about why that could be challenging. Well, I could have a lot of knobs. I could have a lot of different ways to turn the knobs. And it's not obvious to me that the classical problem of optimizing this knob turning is an easy one to solve. Okay, so I wanted to show you there's a lot that goes into what's promised in terms of a chemistry algorithm. It's very exciting. We are able to do this, but there's a lot of stuff that we need to think about. Okay? So let me skip that slide and show you this one. Why would you want to actually do this? So I apologize to all chemists, including myself, because I have half a chemistry degree. When was it that we actually did chemistry where we actually didn't simply go into the lab and try to put something together? Well, here's a case where we have great difficulty with that. Right? If you want to look at nitrogen production or ammonia production, the Haber process takes 1% to 2% of all energy on the planet. Right? Because you put nitrogen and hydrogen together at high pressure, high temperature. Nature does that just fine if you're a gardener and work with your legumes in the ground. They use a catalyst, which is an iron molybdenum catalyst, shown there. And classically, it's very difficult, if not impossible, to understand this catalyst. So the dream is that if your 100-qubit machine can figure out this catalyst, you would have rather transformative impact on this field. Okay. So just to show you, these are some of the things that are advertised, right, for this kind of chemistry simulation. Okay? So how close are we to getting something like this to work? I do want to show you this slide, okay, which shows you the result of the hydrogen molecule calculated on a quantum processor. So we did this a year ago, and in fact, you can see the accuracy is very good, approaching something called a millihartree accuracy, or chemical accuracy in the field, telling you that even though you can solve for the theory curves right now for 2 qubits, if we are able to scale this, you will cross very rapidly this boundary of things that cannot be computed classically. So it is coming together as a technology. Okay. But still, of course, with a lot of questions. So what are the takeaways then for what we've heard this morning? Some new foundational questions. I tried to be honest in sharing with you the level of maturity of the technology, the open physics questions, and the interesting things that are coming out. But what I want to share with you on this last slide is how physicists in hiding are invading like locusts computer science departments. Why are we doing this? Since when have we become so interested in computer science? Because we're really doing physics at this stage. So the real question that's motivating many physicists is how do we stabilize quantum coherence in an open many-body system? We have never probed quantum mechanics at this frontier. We've looked at big things that are quantum, but they're not big in their complexity. There's still 1 degree of freedom or 2 degrees of freedom. And we were always used to this idea that decoherence is simply information which is lost to the environment. You cannot do that in quantum computing. You have some 10 to the 5 degrees of freedom, and you're not losing that information to the environment. Right? Does quantum mechanics work there? Interesting question to think about. Related questions. How can you efficiently sample the information in many-body systems? How can we conceive of machines to treat data fully quantum mechanically? What is really the quantum version of machine learning or big data science? How do we parameterize, verify, and validate the information capacity of a large quantum system? You have a data sheet for your classical computer. I don't know what the data sheet looks like for a quantum machine. What is the role of entanglement? So I set you up with this picture of the little blue things in the universe showing entangled bits. It's not obvious how much entanglement you really need for a quantum computation. So in fact, when you run Shor's algorithm, it's not the entanglement. That's a direct resource. You sample entangled states, but it's the periodicity which allows you to get the Fourier transform. So that's a rather open question. What resources do you really need to build a quantum machine? And how do we express this advantage? This idea that I was telling you, once you have the right classical resources, how do you factor that into your understanding of the power of a quantum machine? So again, what I want to end with is a very positive note, saying that even if these problems are challenging, for sure we will get something valuable out of this endeavor. Because, at least with physicists, I don't think we've solved the theory of all of physics in 1913. That would be rather smug, even though we are sometimes like this as physicists, but that would be rather smug to say that the quantum mechanics of Bohr in 1913 has solved all the problems. I don't think we've looked at physics at the complexity frontier. So this endeavor, ultimately, I think, will teach us something new about highly entangled systems. So I'd like to stop there and take your questions.